Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying methods of differentiation lecture 2. So we'll be talking about substitution, parametric differentiation, differentiation of one function with respect to another function and successive differentiation. Okay. So let's begin a lecture with the substitution, and if you remember from differentiability lecture, we talked about derivatives of inverse functions. We didn't know how did we derive them, but we remembered them, right? So in this lecture, we'll be deriving them with the help of two methods. So the first one is the obvious one, that is first principle. So let's derive sine inverse x derivative with the help of first principle x. So we have fx equals to sine inverse x over here. So if you want to calculate f dash x plus, that would be limit h approaches 0 sine inverse x plus h minus sine inverse x divided by h, right? Very basic formula. Now, if I take x plus h as sine A and if I take x equals to sine B, right? Now, what would happen? This would become limit h approaches 0 sine inverse sine A minus sine inverse sine B divided by h would be sine A minus sine B, right? H would be x plus h minus x, that would be sine A minus sine B, right? Now when we are saying h approaches 0, that means sine A is approaching sine B, right? What is h? H is nothing but x plus h minus x. So when we are saying h is approaching 0, we are saying that sine A is approaching sine B, and when we are saying that sine A is approaching sine B, we are simply saying that A is approaching B, right? So can we replace h approaching 0 with A approaching B, right? Now, if you simplify this further, this would become limit a approaches b. Sine by sine a would be a. This would be b divided by sine a minus sine b. Now, this is nothing but sine c minus sine d formula, right? Sine c minus sine d. So, this would become f dash x plus equals to limit a approaches b, a minus b divided by sine c minus sine d formula. That would be 2 cos a plus b by 2 dot sine of a minus b by 2, right? Now if you look at this one and this one, this is a standard limit, right? When a is approaching b, basically this is approaching 0, this is also approaching 0, that means this becomes 1 only. So it becomes limit a approaches b 1 upon cos of a plus b by 2. This is our f dash x plus. Now a is approaching b, so basically when we take the limit, we can simply write a equals to b. So let's write it as b only, right? This becomes b only. So finally what we have got, f dash x plus equals to 1 upon cos b, right? Now initially what was our substitution? Our substitution was x equals to sine b. This was our substitution, right? Here. Now when x equals to sine b, we can simply say that cos b would be under root 1 minus x square, right? Simply. So f dash x plus would be 1 upon under root 1 minus x square. So this was the way through which we can find out the value of derivative of sine inverse x, right? Now that was the first method. We did use the substitution, but we still use the first principle method. Now let's use the substitution directly without even using the first principle and derive the formula over here. Okay. So we have y equals to sine inverse x, right? Now let's take the substitution. We can take x equals to sine theta. Okay. Now in this case, y would become sine inverse sine theta. That would be theta only, right? Now what we have to calculate eventually, we have to calculate dy by dx, right? This is our purpose. So if we differentiate with respect to x on both sides, we'll be getting dy by dx equals to d theta by dx. How do we get d theta by dx over here? We can get it from here. Okay. So x equals to sine theta, then dx by d theta would be cos theta, right? So basically d theta by dx would be 1 upon cos theta, right? So we can use this over here. We'll be getting dy by dx equals to 1 upon cos theta. Now what was our original substitution? That was x equals to sine theta. Now, can we replace cos theta in terms of x? Yes, we can do that. So that would give us dy by dx equals to 1 upon under root 1 minus sine square theta, right? So that would be under 1 upon under root 1 minus x square. So this was the method where we didn't use first principle, but we still use the substitution method and derive the formula, right? Now, similarly, you can derive all these formulas with the help of the second method or first method. That's your choice. But eventually, you have to remember all of these formulas. Now, these are some standard substitutions which you have to remember, and you'll be using them once again in integral calculus and also in coordinate geometry. Now, the main idea behind substitution is to make the expression simpler. You don't want to differentiate or integrate under root statements, right? You don't want to do that. So that's why we'll be using substitutions for such cases. These are some standard ones which you have to remember. Okay. And now let's solve this question. We have y equals to tan inverse under root 1 plus x square minus 1 divided by x. And we have to find the derivative of y at x equals to 1. Now the obvious substitution over here is x equals to tan theta. Why? Because that would give us under root 1 plus tan square theta. That becomes under root sec square theta. That comes out as sec theta only, right? So we have y equals to tan inverse under root 1 plus tan square theta, or I can directly write it as under root sec square theta minus 1 divided by tan theta, right? Now this becomes y equals to tan inverse modulus of sec theta minus 1 divided by tan theta. Why modulus? Because anything under root or having square, it comes out as modulus because under root is always positive, right? Now, when we say x equals to 1, we say that tan basically theta is pi by 4, right? Now, when theta is pi by 4, that is in the first quadrant, we can simply write modulus sec theta as sec theta only, right? So we have y equals to tan inverse sec theta minus 1 divided by tan theta, right? Now we can convert this into sine cos. That would become tan inverse. This is 1 upon cos theta minus 1. That becomes 1 minus cos theta divided by cos theta multiplied by sine theta by cos theta. That becomes sine theta, right? We can further simplify this as tan inverse 1 minus cos theta is 2 sine square theta by 2, and sine theta becomes 2 sine theta by 2 dot cos theta by 2, right? So this and this and this gets cancelled out. What we've got? Tan inverse tan theta by 2. This is theta by 2 only. Okay. Now what we have got? We have got y equals to theta by 2 after doing our substitution. Now the interesting part over here is we have to calculate dy by dx, right? So dy by dx would be 1 by 2 d theta by dx, right? Now how do we find out d theta by dx? We can find out from this substitution. We have x equals to tan theta. So dx by d theta would be sec square theta, right? So d theta by dx is 1 upon sec square theta, or you can say cos square theta. Okay. So dy by dx equals to 1 by 2 times d theta by dx, that is cos square theta. Now theta is pi by 4 over here. So 1 by 2 into that would be 1 by root 2 whole square. So 1 by 4 is the answer. Now a lot of people do one mistake over here. So in this question, what we have been asked? We have been asked dy by dx at x equals to 1, right? This is what we have been asked. What we have done is we have written y in terms of theta after doing the substitution, right? Now they assume that when this is true, this has been asked, we can write this as dy by d theta at theta equals to pi by 4. Seems fair. Seems correct only, right? Dy by dx at x equals to 1. That means dy by d theta at theta equals to pi by 4. But this is wrong. Why? What kind of substitution we have done? We have done x equals to tan theta. So first of all, what we have to do? We have to find out dy by d tan theta, not d theta. We have to do dy by d tan theta. In that case, we'll be able to find out the correct value. Now that was one approach. Second approach would be, you can modify this one. Dy by dx can be written as dy by d theta multiplied by d theta by dx. Now in this case, you'll get the correct answer, right? So you don't have to do this. You have to use the substitution, actual substitution. When we are saying dy by dx, we have to replace x over here. That would give us dy by d tan theta and not d theta, right? So this is wrong. You have to do this one or this one. And now let's talk about parametric differentiation, and it's a very simple topic. Let's say y equals to sine theta and x equals to tan theta, right? And we want to calculate dy by dx over here. How do we do that? We can simply multiply and divide by d theta over here, and we can write this as dy by d theta divided by dx by d theta. Now you can calculate this one, you can calculate this one and divide them, and you'll be able to get dy by dx. But how are we able to do that? How can we divide by d theta in both numerator and denominator? How do we do that? Is it linear just like numbers? So let's see the theory behind that. So if you remember from the basics, dy by dx is nothing but limit delta y and delta x both approaching 0, delta y by delta x, right? Now if I write delta y by delta theta multiplied by delta theta by delta x and limit delta y delta x delta theta approaching 0, it's still valid, right? So that's why we can write this in this format. Okay, it's still valid, that's why we can write this in this format. Okay, you won't be able to do that for the higher order derivatives. And now let's solve this question. Find dy by dx if x equals to a times theta minus sine theta and y equals to a times 1 minus cos theta. Now both x and y are given in terms of a parameter theta, and we have to calculate dy by dx. Now dy by dx can be written as dy by d theta divided by dx by d theta. Okay. Now dy by d theta would be, we have y equals to a times 1 minus cos theta, right? So dy by d theta, that would be a sine theta, right? And we have x equals to a times theta minus sine theta. So dx by d theta, that would be a minus a cos theta. Okay, so that gives us a times 1 minus cos theta. Now if you want to calculate dy by dx, we have to divide both of them. So we have a sine theta dy by dx equals to a sine theta upon a times 1 minus cos theta. This gets cancelled out. Now sine theta can be written as 2 sine theta by 2 dot cos theta by 2 divided by, this is 2 sine square theta by 2. 2 gets cancelled out. Sine theta by 2 gets cancelled out. So what we have got eventually, cot theta by 2. Okay. And now let's talk about differentiation of one function with respect to another function. And it is exactly similar to parametric differentiation. Let's say we have one function as u equals to fx and v equals to gx as the other function. Okay. Now we want to calculate du by dv, basically differentiating u with respect to v. Now we'll do the exact same thing which we did in parametric differentiation. That is du by dx divided by dv by dx. Now I can simply say that x is a parameter over here, right? This function is defined in terms of a parameter x. So that's why we have included dx and dx over here, right? Same thing, exactly same thing, right? Let's do one question to understand this. We have tan inverse under root 1 plus x square minus 1 divided by x as the function, and we have to differentiate this function with respect to tan inverse x, right? Now if you remember that this function is same as this one, right? And what we did over there, we took the substitution x as tan theta, right? Now, after doing the substitution, we got y equals to theta by 2 under the assumption that modulus of sec theta is sec theta only, right? Basically, all thetas are in first quadrant. We are assuming that over there, right? Now, we have got this one. Ultimately, we have to calculate dy by d tan inverse x, right? Now, I can modify this one as dy by dx divided by d by dx of tan inverse x, right? And now if we talk about dy by dx, we have to modify it once again. Dy by dx equals to dy by d theta divided by dx by d theta, right? Now dy by d theta can be calculated from here. That comes out to be 1 by 2, right? Whole divided by dx by d theta. Dx by d theta comes from here. That comes out to be sec square theta, right? Now x equals to tan theta. So sec square theta would be 1 plus tan square theta. That is 1 plus x square. Okay. So this comes out to be 1 plus x square. So ultimately we have got dy by dx as 1 upon 2 times 1 plus x square, right? Now, if we talk about this portion, d by dx of tan inverse x, we all know that this is 1 upon 1 plus x square, right? Now, what we have to do, we have to calculate dy by dx. Basically, 1 upon 2 times 1 plus x square divided by 1 upon 1 plus x square. This gets cancelled out. What we have got? We have got 1 by 2 as the answer, right? And now let's talk about successive differentiation. And although it's not a part of PGDBA syllabus, but let's have a basic understanding of what it means. Okay. So until now we have studied dy by dx only. That is first order derivative. Right? Now if you want to calculate dy dx of dy by dx, we have to write it as d2y by dx square. It doesn't mean that we are squaring over here. It's just the notation, nothing else. Right? If you want to calculate one more derivative of this one, we'll be doing d by dx of d2y by dx square. Now this comes out to be d3y by dx cube. Again, it's not cube, it's nothing, it's just the representation over here. Now one interesting thing over here is, in this case, dy by dx was equals to 1 upon dx by dy, right? We use this many times, right? We could do that because it came from delta y by delta x, limit delta y delta x approaching 0. We could do that because of this, right? Now when we are calculating d by dx of dy by dx, we won't be able to do that. This is d2y by dx square. We cannot write this as 1 upon dx square by d2y. We cannot do that. Because of this, we lose the linearity over here. We lose the linearity over here. That's why we're not able to do that. In this case, everything was linear. That's why we were able to do that. Over here, we cannot do that because we lose the linearity once we introduce the second order derivative. Okay. So these are the few points which I wanted to discuss about successive differentiation. And this marks the end of methods of differentiation. Let's meet in the next lecture for application of derivatives. Thanks for watching.